Hi all, welcome to part 13 of the video lecture on counters. So far we discussed many variations of the counter, starting with the asynchronous counter, then we moved on to synchronous up counter, down counter, up and down counter using a single circuit, BCD counter, right? These are all the things we saw so far. Now it's time to explore something called a counter which can count with some of this in between. It's not in a counting in a continuous manner. In between, some of the states are invalid or they are not used. Accordingly, the counter should be able to count. So that is our requirement. So what is written? A circuit with the n flip flops. By default, whenever I am having a circuit with n flip flops, basically it is an n bit register. So it will go through some 2 power n binary states, right? N bits are there. So starting from 000 n bit to 1111 some n bits. Okay, I mean n bits. So it will be counting some 2 power. So this also n bit. Okay, like that I mean. So that it will count some 2 power n states. So for example, 3 bit counter. 3 bit counter means it will count from 0 to 7. Right, 0 to 7 means 8 states. That is 2 cube. Like that. Okay, so that is one question that you can expect. How many flip flops are needed to implement a 2 power n counter? Okay, so sometimes they may ask you, and you should explain, and you should be able to justify why it is so. So the question is, how many flip flops are minimum so specifically they can ask you T flip flop or JK, whatever it is, same answer will be there. Needed to implement modulo or mod 2 power n counter. So modulo 2 power n counter means what? Modulo counter or mod 2 power n counter means 2 power n states are to be counted, right? States are there. Now for 2 power n states, it's achieved through n bit. So it's nothing but an n bit counter. N 0 bits to n 1 bits, it will cover the 2 power n states. So for it's basically counter is nothing but a register, n bit register. And for n bit register, basically one flip flop can store a single bit, right? So one flip flop is nothing but a 1 bit register. So n bit register is achieved with the n flip flops. So like that, they can frame a question for you. Okay, so just keep that in mind. There are occasions when a sequential circuit uses fewer than this maximum possible. So if there are 2 power n possible states, the straightforward binary up counter, binary countdown counter, those things, the implementation we know. But sometimes it will be less than that. For example, in BCD counter, we saw that it is not going for that 16 states, right? It's even though it is a 4-bit counter, it is going through 10 states only. So like that, so there also we have the benefit. The states are continuous, but in between some of the states may be unused, right? States that are not used in specific sequential circuit are not listed in the state table. So sometimes they may give you the sequence, sometimes they may be the state table. So by observing the state table, you can understand that some of the states are missing. That means they are not valid according to this particular counter, right? In simplifying the input equation, the unused states may be treated as don't care. So just like what we saw done in BCD counter, the states like from 10 to 15 we treated as don't care, and then we simplified the circuit. The same thing you can apply here also. Right, so what you have to do with the unused state, you have to treat as don't care. So that is the safest way. But you can make it meaningful also, that also we will see. So it is important to realize that once the circuit is designed and constructed, outside interference during its operation may cause a circuit to enter into one of the unused state. So some of the states are unused, so there is no guarantee that it will always go through valid states. Sometimes it may go to unused state for sure. Now once it reaches unused state, whether it is able to come up from that situation, like whether it is able to come back to some used state, or it will simply stick on that unused state. So that is the question we are facing. So in that case, it is necessary to ensure that the circuit eventually goes into one of the valid states somehow, so that it can ensure a normal operation. So Okay, so even though it is trapped into some unused state, somehow it is enter into some valid state. Otherwise, if it is simply roaming around the unused state, there will not be any use with the circuit. So that you have to ensure. Otherwise, if the sequential circuit circulates along some unused state, and there will be no way to bring it back to the intended sequence of transition, that we don't want, right? So if the unused states are treated as don't care condition, then once a circuit is designed, it must be investigated to determine the effect of the unused. So this is important after designing the circuit. So for whenever you are designing the circuit, you can treat them as what called don't care. So don't care, whenever it can be 1 or 0. So for getting the largest grouping or for simplifying this circuit design complexity, we will treat this don't care as 1 whenever needed, and those things, whether that assumption is correct or not, that you have to analyze after creating the circuit. Okay, then the next state from an unused state can be determined from the analysis of the design circuit, and we will see how to analyze and how to deal with the unused state. Okay, so counter with the unused state has an example. See here, you can see that some state table is given where the count is present values. If you are observing, this is your 0, this is your 1, this is your 2. Now this 3 is missing. 0, 1, 1 is not there. See, next combination is 4, right? Then it is 1, 0, 1, that is 5. Then 6 is there. Again 7 is missing. So it is, if I am expressing it with a state diagram, I can see like it start with 0, then it is going to 1, then it is going to 2, then it is going to 4, not 3. So 3 is something unused or invalid. From 4 it is going to 5. Okay, then from 5 it is going to 6. Now again there is nothing like a 7, it is going back to 0, like that it will go. So in between there will be something called a sorry for that. So 4 it will go to 5, and from 5 it will go to 6. So what will happen with the 3? That is the first question. Similarly, what about this 7? Okay, we will see that. So that's a question mark for us. So anyway, this kind of a counter is what we are having. So sometimes they may give you, given the state sequence, right, like 0, 0, 1, 2, 4, 5, 6, design the counter. So this is the type of question you can expect mostly, or they may give the state table also. If this is the case, you know how to draw the state table and accordingly how to proceed. So it's a very simple thing, right? So here if you are observing, you can see that this B and C, the least significant 2 bits, they are counting like a 0, 0, 0, 1, 1, 0. Then 1, 1 is missing. After 0, 0, 0, 1 and 1, 0, it is going to 0, 0, 1, 0, 0, 1 and 1, 0. So that pattern is being repeated. Here for the first half it is 0, then 1. So that is explained in here. As an illustration, consider the counter specified in the next slide, right? So this is slide, okay. So the counter has a repeated sequence of 6 states with the flip-flops B and C repeating from 0, 0, 0, 1, 1, 0, then 0, 0, that you saw. And the last flip-flop is alternating between 0 and 1 every 3 counts, okay. So the count sequence of the circuit is not straight binary, and you can see that 2 states are missing, like that 3 and 7 is missing, right? 0, 1, 1 is missing, and 111 is missing, are not included in the counts. The notice of the JK flip-flops, the choice of the JK flip-flop results in the flip-flop input condition listed in the table. Anyway, we are trying to implement using JK, but it's very easy to implement using T. If in the question nothing is mentioned, you can assume T, but you should know how to implement using JK also, right? So this is where we will depend on that excitation table, as this count sequence you have to implement using because when it comes to the normal binary up counting and down counting, and that time, okay, anyways, we didn't saw the state table implementation for JK, right? JK flip-flop implementation we saw for that up and down counter and up counter, but with that observation we draw it, okay, fine. But here we will see the correct implementation, just like TT flip-flop is just a single input, it is either 0 or 1, so it is easy to fill. But for JK input, in more than one case, that transition of the output will occur, like from 0 to 0 or 0 to 1. Accordingly, you have to now remember the excitation table. So I don't know whether you remember or not, let me tell you. So excitation table is basically about we will see that. Okay, so here we listed out a state table, like after 0 the next state has to be 1. Okay, after 1 the next state has to be 2. Okay, after 2 next state has to be 4, not 3. Okay, after 2 next state is 4, then after 4 next state is 5, after 5 next state is 6, after 6 it is not 7, it is 0 again. So like that we have the table. Okay, now what about this J and K? So just look at the excitation table. First, how this bit A is changing, and this is the present value of A, and this is the next value of A. I am denoting like small n means the next state of A, small p means the present state of A. Or let's have a different, the both are A only, but still A at a time t and A at a time t plus 1, something like that. Okay, so the output of the particular flip flop, we need a change, like it can be 0 0 1 0 1 1. So 4 types of transitions we are having, and for each of this transition, what is your J and K? So the first change is like a 0 to 0, 0 to 0, the two in cases are there. One is like a retain or no change, so that the input is something like a 0 0 retain. And another case is resetting the circuit will also make A output in the next clock cycle as 1. So it is something like a 0 is fixed for J, and K can be 0 or 1. Both will achieve this transition. Okay, so this is something we typically write it as 0x, don't care. Similarly, 0 to 1 transition, this corresponds to toggling, or this corresponds to setting the circuit. So this is something like a because I want 1 finally in the output, so setting the circuit. So it's something like a 1x, right? So accordingly this will be x1 and this will be x0, I mean don't get 0. So just understand how it is working. If you still have any doubt, please watch some previous video to understand the excitation table. So with the help of the excitation table, we filled this, right? So it's very important. So if you are looking at this A transition, A is changing from 0 to 0. For 0 to 0 change, J and K, I mean J and JK1, it should be 0x. That is what is written, right? Similarly, then B is changing from 0 to 0. Again, it will be 0x. Okay. And if you are looking at C, the bit C is changing from 0 to 1. 0 to 1 transition, the input to J and K should be 1 and X. Okay, so that is how we are writing the table. Now, is that idea clear, right? Fine. Now, once you have this, you can simply use a K-map and you can simplify the circuit, and it's a 3 input K-map is needed, right? Because 3 bit register we are having, 3 inputs are there, so there will be 8 cells, and the inputs are like A, B, C. So 0 0 0 1 1 0 1 1 and 1. We are just looking at this JA. Let's see what is this JA. Okay, so this JA, the minterms are like so look at the present state and accordingly fill the minterms. So this corresponds to 0, this corresponds to 1, and this corresponds to 2, and this corresponds to 4, 3 is missing. This corresponds to 5, this corresponds to 6, 7 is missing. So which are all missing? Like 0, 1, 2, 3, 4, 5, 6, 7. So which are all the terms that are missing? Missing 3 is missing, put it as don't care. 7 is also missing, put it as don't care. Okay, so that is the way you have to simplify. Other bits you can see, say like 2 is 1, 2 is 1. Other bits are 4, 5, 6, they are already don't care. 4 is don't care, 5 is don't care, 6 is don't care. Yeah, that about it. Now if that is the case, how can you simplify? The largest grouping possibly something like this. And what is the term corresponding to it? This A vanishes and B remains 1. C also vanishes. So this is just B. So we got like this is the simplification for JA. JA we got as B. Similarly, you can simplify for KA, right? JB, KB, JC, KC. So 6 inputs were there. So that is the benefit. If you are using toggle flip flop, just T flip flop, only 3 inputs you have to minimize. Then it is very easy for you to implement the circuit. Okay. Here you have to verify 6 inputs. And finally you got the expression for all the 6 inputs of the circuit JA, KA, JB, KB and JC, KC like this. Okay. So that you have to verify. You have to do it yourself, right? You have to simplify as a practice for K-map. You please simplify all of this expression and see whether you are getting it. Only thing is in the missing terms we are putting don't care and then we are minimizing. Okay, and otherwise using excitation table also sometimes we are getting don't care, and don't care group only if it is needed. So this is how you can draw the circuit, we saw like for the first flip-flop which is giving this A as output, this corresponds to J and K, and J and K we got like a B. So this B we are connecting here. So this is our B, right? So that we are connecting to this J and similarly this J's B was C, I think. So C is getting connected, and similarly this was 1. I mean KB. Okay, KB is 1, J B C, right? You can see here. So like that you can understand the diagram fine. So the diagram is clear, I think. Now the last thing is like so this is a state diagram we are having. State diagram we observe like a 0, it is going to 1, then 2, then 3 is missing, 4, then 5, then 6, back to 0. Now this is our missing states, that is our state number 7 and state number 3, and that case how it will be. So now we already know the circuit by taking the inputs which are missing as Don gear and all, we got an expression for the circuit, and it's a minimal expression also, because when we minimize it using KMF, we assume that this Don gear is 1, and accordingly we did that minimization. Now so definitely we have the best implementation with us, like that, let's hope. But to make it very precise and very accurate, what you have to do, you should ensure that this, in any case, definitely the circuit may go to that invalid state. So if it is reaching that invalid state, somehow it should be reach any of the valid state, then only it can go through the actual counting procedure. So is it possible for us to achieve it? Okay, let's see that. So now the bits are naming like A, B, C, right? These bits are like A, B, C. So here also A, B, C, and you can see that what is happening to bit A. Bit A is actually it was 1 when it comes to 7, and that same bit how it is changing, that is a question. Okay, so this is in the current state. In the next clock cycle, how it is changing, and you know this change is determined by our JA and KA input, and you hope you remember this JA and KA both are B, like that we simplified the expression, right? So both of them are, you can see that here JA is equal to B and KB is equal to B, so KA is also B. So like that we have the circuit. Now what is B according to us from the current state? B means the B in the current state, right? So currently B is 1. So if B is 1, you know, correspondingly this A bit will, JA and KA is now they are in the toggle mode, right? So that this A bit will, I mean because of this case, this A bit will change to 0. So this is the conclusion, fine. So you got this last bit, sorry, A, B, C, this 8th bit you got, how 8th bit is changing. Similarly let's see what happened to the Bth bit. So Bth bit is changing from Bt to Bt plus 1, and presently, so the present combination is like you know, this is how I am taking AT B, this it in the teeth clock cycle, the bits I am denoting like this. If that is the case, suppose 7 is an invalid state. From this invalid state, where it is going? That is my question. I saw like this bit is changing like this, okay? Because this J, K, they are found to be 1, so they are in the toggle mode. So definitely the next clock cycle, after the next clock cycle, this bit will change. Now what about this bit? Okay, so that is a second observation. That bit is right now it is 1, and to what it is going? That is my question. So let me see what is my JB and KB. And you know, JB was our C and KB was 1. JB is equal to C and KB equal to 1. So what is your C? Currently C is actually, C bit is 1. Okay, so in effect we are getting toggle again. So again toggle, and this toggle says that this 1 should be changed to 0. So that is why, and so here also this says the toggle. Okay, so the toggling is happening, and this bit is also changing to 0. Now what about the Cth bit, right? Cth bit, Cth bit, you know, in the current clock cycle it is 1, and to what it is changing? That is my question. And for that I am observing my JC and KC, and you know, JC was like B complement and KC was 1. B complement, right? So currently what is your B? Your B is currently 1, so its complement will be 0. Okay, similarly this KC will be 1, that is fixed. So 0 1 corresponds to the 0 1 corresponds to reset. So last case only resetting is happening, and resetting will also change this 1 to 0. So this 1 is getting changed to 0. So here these two things are actually toggle. toggle, and this transition is because of resetting the circuit. Okay, anyway, what we observed is after 111, which is an invalid state, so in any case, due to any error, suppose a circuit reaches this 111, after applying one clock cycle, after the next clock cycle, by analyzing the current circuit, I understood that I am moving on to 000. So definitely if it is reaching any invalid state, it will come back to the valid state immediately, that is for sure. Similarly, you have to analyze for 3, and you know that you can see that after this 3 it is going to this 4. Whatever it is, any state is fine. We just want to reach some valid state if it is reaching invalid state at any point. Okay, so that is our requirement. So that is happening here. That's 3 case, you please analyze yourself. That's 011 case. I request all of you to analyze yourself. Okay, anyway, that is happening. So it is something very valid way of understanding it. Anyway, so now you know how to come up with a synchronous counter for any random sequence in the X, and they can give you like a even number counter, anything they can give you. So which are all the states which are unused or invalid, please treat them as don't care and proceed with the simplification and come up with this. So this part is important. Once you get this part, you can simply implement, right, using some small circuit like that. Circuit diagram is equally important, otherwise you may reduce some mark, we don't know, but anyway this much is enough according to me. But sometimes those who are evaluating may look at that circuit diagram also. Okay, and also finally, if we can show this how that state transition looks like for invalid state, it will be very good. But look at the mark, and if needed only you do it, otherwise just implement the circuit. That much will be enough. So based on the question you can do that. Anyway, hope you get an idea about it. Yeah, thanks for watching, and subsequent things we will see in the next video.